Good day everyone, my name is Lawrence Macabenta, and today in this video lesson we are determining whether entropy will increase or decrease if the temperature changes, the phases, and the number of molecules. For our learning objectives, at the end of this video lesson, a learner should be able to determine the signs of entropy change for a reaction and calculate the value of entropy change for a reaction. So how do we determine whether entropy will increase or decrease? Before we move on to that, we have to know what entropy is. Entropy, it is a scientific concept that is mostly associated with the uncertainty, randomness, or disorder in a system. An ordered system would have a low entropy, and the disordered system would have a high entropy. As shown in the graph below, we have solid, liquid, and gas. We can see that from solid to liquid to gas, it would have an increase in entropy. And from gas to liquid to solid, it will have a decrease in entropy. This is because the states of matter have different molecular structure. The solid have a very tight and ordered molecular structure, so the particles are tight in the box. The liquid is a bit loose, but we can see that there is still a little bit of order. While the gas, the particles can move around and bounce around inside the box, so it will have a higher chance of high entropy. Next is the factors that affect the changes in entropy. So the first one would be the factors that increases an entropy. We have the increase in the number of molecules. So in the example, we have 3 molecules in the reactant and 4 molecules in our product. So there we have increased the number of molecules from reactant to product by 1 molecule. Next is the increase in temperature. So increase in temperature may affect the phase transitions of a substance. For example, we have ice. If the temperature gets high enough, the ice will melt through melting. There is a melting point from solid to liquid. We also have evaporating from liquid to gas and dissolving from solid to gas. Next, we have uh, factors that decreases an entropy. So it's kind of like a reverse of the first factors. So in this one, instead of increase in the number of molecules, we have decrease in the number of molecules. In the example, we have 4 molecules in our reactant and 3 molecules on our product. We decrease the number of molecules from reactant to product by 1 molecule. The next one is a decrease in temperature. Another example of this is ice. So, liquid may enter a freezing point when a temperature gets low enough. So, it turns to liquid to solid. We also have condensation as another phase transition in decreasing entropy. So now we can proceed to some practice problems so we can predict if entropy will increase, decrease, or stay the same. Grab your pen and paper and let's get started. Predict the signs of entropy change. Let's take a look at these examples. So here we have the factors to look at. We have the change in phases of solid, liquid, and gas, and number of molecules. In here we have the chart or where it says that increase in temperature will lead to increase in entropy. So number one, we have H2O liquid as our reactant and H2O gas as our product. So to identify which one's the product and which one's the reactant, we have to look at the arrow. The one it's pointing to is our product, and the one it's not pointing to is our reactant. So in our reactant, we have, so in change in phases, we have liquid to gas, which means here, if we look at here, it means that it will have an increase in entropy. If we look at the number of molecules, we have one molecule going to one molecule. So it's pretty much the same. So we're gonna look at the change in phases, liquid to gas, which means that number one will have an increase in entropy. So number two. For number two, we have AQ meaning aqueous phase. So take note that aqueous phase is here between liquid and gas. It is in state of matter dissolved. So looking at the state of matter, we have AQ here going to solid. And the number of molecules in our reactant, we have two molecules. And our product have only one molecules. Which means that AQ going down here in our chart, it means it will have a decrease in entropy, and since decrease in entropy is also decrease in number of molecules, so we go from two molecules to one molecule, we can conclude that number two will have a decrease in entropy. So number two. Number three is a bit tricky. You can pause if you want to try, but we'll start now. So in change in phases, we're going to, we have in our reactant solid and gas, and in our product we have solid. So in this one, we're going to, we have here in our reactant we have gas, and here in our product we only have solid. So we're going from gas to solid, which means that it will decrease in entropy. Now we'll take a look at molecules. So in our reactant we have 4 molecules and 3 molecules. So here. So we will add it. 4 plus 3 is equals to 7 molecules. Going to here we have 2 molecules. So in our product we only have 2 molecules. So since we go from gas to solid and we have a decrease in molecule, we can conclude that number 3 will have a decrease in entropy. So pretty simple looking at changes in phases. So and looking at the number of molecules. So in number of molecules, if it has an increase in molecules, it will have an increase in entropy. So we have here mostly decrease in molecules 2 to 1 molecules, 7 to 2 molecules. Now let's take a look at a few more examples. Number 4. So for this last two, you can pause and try it yourself. So you can really learn it. I'll wait for a few seconds. Okay, let's start. So here in number 4, in changes of phases, we have gas, our reactant, to gas, our product. So there's no change in phases. In number of molecules, we have 1, 2, 2 molecules of for our reactant and 2 molecules for our product. So nothing changed. Gas to gas. 2 molecules to 2 molecules, which means that our entropy will stay the same. So the value might not be exactly zero when we calculate it, but it will be pretty close. So number 5, we have in our change in phases, solid to gas, which means that it will increase in entropy, but we have to look at the number of molecules as well. So we have 1 molecules to for our reactant and 1 molecules for our product, which means that by looking, our number of molecules didn't change, but the phases change from solid to gas, so it will have an increase in entropy. So those are how we predict or determine the change or the signs in change in entropy. Next topic of us is how do we calculate entropy change or delta S. So in learning entropy, we must be able to do first is predict the sign of entropy change. Predicting the sign of entropy change is what we did just now. Now for the next one, we have calculate for the value of entropy change. And to calculate this value, we have the equation that is given below. The delta S or change in entropy is equal to the sum of entropy of product minus the sum of entropy of reactant. In this equation, we're also going to use a standard entropy values chart of some elements and some compounds. Note that this is not a complete list. The list is actually pretty long, and I can only fit a few in it in this presentation. Now, I believe that uh, demonstrating it will be easier to learn than just saying it. So let's get to calculating for entropy change. Get again your pen and paper and let's get started. calculating the value of entropy. So in here, we're gonna use the equation. Change in entropy is equals to uh, sum of entropy of the product minus the sum of entropy of the reactant. We're also gonna use the table that I have shown you earlier, the standard value of entropy chart. So number one, we have H2O liquid as our reactant and H2O gas as our product. So basing on this equation, we're gonna have to start on our H2O gas. So the value of our H2O gas is 188.84 minus the value of our H2O liquid. In our chart, the value is 69.95. Pretty easy, we're just gonna minus 188.84 minus 69.95 is equal to 118.89 joules per molecule Kelvin. This is our sign. So pretty easy. You just get the value on the chart and you use this equation to get the change in entropy. So as you can notice, we go to positive, meaning there is an increase in entropy, which matches our prediction earlier. Number 2. So number 2, we have our product CH3OH liquid. Its value is 127.2 minus the value of our CO gas is 197.7 plus we have 2 molecules of hydrogen 2, meaning we would need to multiply. So close parenthesis here. So 2 times the value of hydrogen, which is 261.4. So we're just gonna use PEMDAS. So 127.2 minus 197.7 plus 2 times 261.4. Sorry, wrong. So the value of hydrogen is 130.7. So 2 times 130.7, we would get 261.4. Now we just add it. Parentheses, in close parentheses first. So copy minus 197.7 plus 261.4, we would get 459.1. 127.2 minus 459.1, we would get negative 331.9 joules per molecules Kelvin. So, number 2, this is our answer. A bit longer than number 1, but it's pretty easy to understand. So, same equation. The only difference is we added 2 of our reactants. So here, And we have two molecules of hydrogen 2. So we multiply the value of hydrogen 2 by 2. So 2 times 130.7 is 261. Then proceed to the usual PEMDAS. For our last example, we have CH4 gas plus 2 oxygen gas CO So here, our product is the one that the arrow is pointing to, and by the equation, we're gonna start our value here. So CO2 gas is equals to, close parentheses, 213.7 plus, we have 2 H2O liquid, so multiply by 2. 2 times the value of H2O is 69.95, close parenthesis, minus our reactant, we have CH4 gas. The value is 186.3. Remember, the value can be obtained on the chart I provided. Plus, we have 2 oxygen. So, multiplied by 2, the value of oxygen is 205.1. So, it's equals to, copy, 213.7 plus 69.95 times 2 is equals to 139.9 minus, copy again, 0.3 plus 2 times 205.1 is equals to 410.2. So now we're gonna add the end close parentheses. So we have 213.7 plus 139.9 is equals to 353.6 minus, here, 500, 186.3 plus 410.2 is equals to 596.5. So we're gonna minus the 2. We're gonna get a negative 353.6 minus 596.5 is equals to 242.9 joules per molecule Kelvin. So this is our longest example. Remember, always minus the reactant to the product. So the value of CO2 here, our product, is 113.7, and then 2H2O. So the value of H2O, 69.95 multiplied by 2. Same here in our reactant. And then follow the PEMDAS rule. Now, for the last part of this video lesson, we have the quiz. It has two parts. Part A, predicting the signs of entropy. So you're just gonna have to figure out if the entropy will increase, decrease, or stay the same. Part B, calculating the value of entropy change. So in this one, we're gonna have to use the equation and the standard entropy values chart. You can do this at home in any pen of paper you like, and we're also gonna be checking it in this video lesson. So just pause to see the questions or the elements. And now for the answer. Let us take a look. So now we're gonna answer the quiz. Quiz A first. So predicting the signs of entropy. So number one. In number one, we're gonna look over the phase first. So we go from solid gas to solid. So we have gas to solid. And the number of molecules. So we have two molecules going for our reactant. We have two molecules, and our product have only one molecules. So gas to solid, it means decrease in entropy, and we also have a decrease in the number of molecules. So the answer to number one is decrease in entropy. Number two, again the phase of the chemical first. So from gas we go to gas. So same, and the number of molecules. So we have one, two molecules for our reactant, and two molecules for our product. So same phase, same number of molecules. So the number two will most likely have the same, will have its entropy stay the same. So again, it might not be exactly as zero in the value, but it's gonna be pretty close. Number three. So our reactant is both gas and our product is solid. So we're going from gas to solid. And the number of molecules, we have here two molecules as in our reactant, and one molecules only in our product. So gas to solid, it means a decrease in entropy, and we also have a decrease in the number of molecules, which means number three will have a decrease in entropy. Number four. So we'll look at the phase again. So from solid in our reactant to gas in our product. Solid to gas. And the number of molecules are the same. So number of molecules are the same. So we're gonna look at the phase. Solid to gas. We know in the chart earlier that solid to liquid to gas will have an increase in entropy, meaning number 4 will have an increase in entropy. Number 5. So number 5, the arrow is pointing to the product. So our product in number 5 is here. And this is our reactant. So in our reactant, we have solid and gas going to solid. So gas to solid. And the number of molecules in our reactant, we have 4 and 3. So 4 plus 3 is 7 molecules. And the number of molecules in our product is 2. Which means in here, gas to solid, so it will have a decrease in entropy, and we also have a decrease in molecules. So number 5 will have a decrease in entropy. Now we're gonna answer quiz set B. It only has 3 items. So number 1, our product, remember the equation, product minus reactant. So the arrow is pointing here. So this is our product and this is our reactant. So the value of our product is 92.9 minus close parenthesis, the value of CaO gas is 39.7 plus the value of CO2 gas is 213.6. We're gonna follow PEMDAS, so 92.9 minus 39.7 plus 213.6 is equals to 53.3. So we're gonna minus 92.9 minus 53.3 is equals to 39.6 joules per molecule Kelvin. This is our answer, 39. 39.6 joules per molecule Kelvin. So in our number 2, we have H2 plus chlorine 2 as our reactant, and our product is HCl2. So our product first, the value of this is 186.2. We have 2 molecules, so multiplied by number 2 minus the value of H, it's 130.7 plus the value of Cl is 223.1. Remember, the values are in the chart that I showed earlier. So 186.2 times 2 is 372.4 minus 130.7 plus 223.1 is equals to 353.8 minus, will minus the 2, the sum of product and sum of reactant. So it equals to 18.6 joules per molecule Kelvin. It is our answer. And lastly, number 3, pretty long one. So we're gonna start with our product first. Here is our product. The arrow is pointing on our product. So the value of CH4 gas is 186.3 plus we have 2 molecules of oxygen gas. So 2 times 205.1 minus CO2 gas. The value of our CO2 gas is 213.7 plus we have H2O. 2 molecules of H2O. So 2 times the value of H2O is 69.95. Follow again the PEMDAS. So 186.3 plus 205.1 times 2 is 410.2 minus 213.7 plus 2 times 69.95 is 139.9. So add the sum of our product is 596.5 minus the sum of our reactant, which is 353.6. So our answer or the value of our entropy will be 242.9 joules per molecule Kelvin. Here is our answer. So remember to look out for a couple of things. The arrow, where is the arrow pointing at? That's where our product is, and by stated by our equation, the product minus the reactant. Also watch out on the number of molecules, just like this one, 2 HCl. So just multiplied by 2 the value of HCl. And follow PEMDAS. Also, don't forget the unit. Joules per molecule Kelvin. That is all. I hope you learned something from these video lessons, and stay safe and have a blessed day. Goodbye.